Welcome to the video on the projectile motion. Now in this video, I'm going to establish the problem statement for a typical problem on projectile motion and what is given generally. And I'm also going to take you through the part which requires finding certain variables. Yeah. So first, in a typical problem, what will be given will be the initial velocity in the x and y direction, and what will also be given to you will be the initial displacement. So when we say initial, that is at time t equal to 0. So in summary, initial at time t equal to 0, the velocity will be given to you in the x and y direction components, and also the initial displacement will be given. And eventually, what we are required to find is typically, for example, it could be what is the time after which the projectile hits the ground. So we have to find the time at which the projectile will hit the ground. And there could also be a question like how far does the projectile land from its launching site, which means we have to find out the horizontal distance it covers when it falls away from the launching site. So let's see how does it look like on the graph. So in the picture, I have drawn a projectile path, which is the same as the parabolic path. And what will be given to you will be, if you see, for example, if I take an example of somebody standing on the roof of a building and such that the height of the building is h meters. So from the top of the building, if somebody is throwing a ball, let's say, and with a initial velocity magnitude given as vi meter per second, and the throw is such that the velocity makes an angle of theta I degree with respect to the horizontal. So few things, as I mentioned, are already given to you: initial velocity magnitude and the direction which it makes with the x-axis, and also the initial displacement is given to you, which is the height of the building from where the object is thrown. Now, as we know, it will be executing a projectile motion, and although it may not look like a perfect parabola, but I have tried my best. And let's say after some time t, the ball hits the ground at point P, as I have shown. Now, in terms of what you will be asked, could be anything starting from, for example, in option A, at what time t the ball hits the ground at the horizontal, and also what is the length OP. So that's the horizontal distance the ball has covered at the end of its projectile motion. There could be also many more questions that can be asked based on this. For example, what's the value of the acceleration or the velocity at a given time t? And there could be many more. So let's see what are the steps involved in the solution for the problems related to projectile motion. The first and foremost will be to find the general expression for the velocity. So within that, let's see what are the steps. So the vector acceleration A will be equal to minus g times the unit vector j. And g here represents the acceleration due to gravity, and it points vertically downwards. So if any projectile is in its projectile motion, the acceleration A vector will always be pointing in the downward direction. And that's what the negative sign represents over here. It's along minus j axis. Yeah, j is a unit vector along the y-axis. So minus j will be in the negative j direction, and the magnitude will be given by g. So the value of g will be 10 meter per second square, and therefore the vector A will be equal to minus 10 times the vector j. And if you remember, the acceleration A is given as the rate of change of velocity. So this expression shows it is time derivative, or d by dt of velocity. Now, henceforth, going forward, I will not be pronouncing the word vector as it is understood to be there. Yeah, so just for convenience and simplicity. So acceleration will be given by time derivative of the velocity, or just changing the sides, we get rate of change of velocity will be the acceleration. And on the right hand side, if I consider 1 in the denominator and then I do a cross multiplication, so I will get dv. So dv times 1, which is dv, will be equal to a times dt. A small change in the velocity will be equal to acceleration times a small change in time. Now, another important concept for applicable for the next step will be, we know that the integration of the derivative is the variable itself. There is also a constant of integration, which I am not interested in showing right now to make it simple, which also means the integration of dt will be equal to t. So if we apply the same logic, the integration of dv will be equal to v. So I do integration on both the sides. On the left hand side, it will be integration of dv. On the right hand side, it will be integration of a times dt. So as I mentioned, for the next step, v will be equal to integration of a times dt. And now we put the value of acceleration over here. So velocity will be equal to minus 10j times dt. And we put all the constant terms outside of integration, and only the variables should be inside the integration symbol. Variable over here will be dt. So on the right hand side, we get minus 10j integration of dt. And as I mentioned, integration of dt will be t. So using the same, we get velocity will be equal to minus 10tj plus a constant of integration. Now the next step is to find what's the value of c. And so let's call this as equation number 1. Now the next step is to be able to find the constant c. How do we find? So at time t equal to 0 in equation 1, what we will get is on the left hand side will be the initial velocity, and the right hand side will be equal to c because t becomes 0. Yeah. So initial velocity will be equal to the vector c. Now, given that c is equal to the initial velocity, but what is the initial velocity? Its value, I mean. This is something we are going to the next step now, finding the value of the constant vector c. So for that, we know the equation. Velocity at any given point of time will be the horizontal component of the velocity, which is given by v cos theta, and v cos theta times I, plus the vertical component of the velocity, which is v sine theta j. So in the question, it will be given to you as one of the input that initial velocity, which means at time t equal to 0, the angle theta will be equal to theta initial, and the velocity will be equal to velocity initial. So what will be given essentially will be the vi and theta I, and therefore with this we can arrive at the initial velocity, which will be given by vi, which is given cos theta I, which you can calculate, times I, plus vi given sine theta I, which is also given, times j. Let's call it as equation number 3. So we now know that equation number 2 should be equal to number 3. Why? That's because constant is equal to the initial velocity, and therefore the next step will be the constant c will be equal to vi cos theta I plus vi sine theta I j. Now, if we put the value of c in equation 1, so that means equation 1 will become something like this. Velocity will be equal to minus 10t times j plus the initial velocity we have seen before, vi cos theta I plus vi sine theta I j. And if I rearrange the terms in such a way that all the terms related to I are on one side and all the terms related to j are on towards the right hand side. So this will look like velocity will be equal to vi cos theta I times I, plus inside you will have minus 10t plus, it should be only one times, vi sine theta I times j. Great. So we are now at the second step of finding the general expression for the displacement. So velocity is time derivative of the displacement. We can write like this. Rearranging the term, it looks like this. D by dt of the displacement will be equal to the velocity. And using the similar logic as the previous one, if this is denominator as 1 and if I cross multiply, then the ds will be equal to v times dt. And then again, using the similar approach, if I put integration sign on both the sides, so it will be integration of ds will be equal to integration of v dt. And as I mentioned earlier, integration of ds will be equal to s, and therefore we get on the left hand side s will be equal to integration of v dt. And if you remember from the previous page, we have the velocity expression. Time now to put that velocity expression in this integral. So we have displacement will be equal to integral of vi cos theta I times I plus in the bracket minus 10t plus vi sine theta I times j times dt. So it's a time integral. That means we are integration with respect to time. Now we need to find the integration of this expression, and then again using the concept that integration of the derivative of time, integration of dt will be equal to t, and also I'm going to rearrange the terms. So this is within the integration for the first term, and then I take the integration for the combined term like this. I can split them in such a way. But first, let's see the integration of this expression. Vi is a constant, cos theta I will be constant, so it will be taken out, and then integration of dt, that will be t times I. And similarly, for the integration of the middle term, if you see the expression, I can take minus 10 outside, it's a constant, so it's minus 10 t, and I can also take the constant j dt. So what's the integration of t dt? So if you remember the identity, integration of x power n dx will be equal to x to the power n plus 1 over n plus 1. So if I apply the same logic with respect to the variable t, it will look something like this. Integration of t power n dt will be equal to t to the power of n plus 1 over n plus 1. Now if I put the value of t as equal to 1, because I can write it as integration of t power 1 times dt, that will be equal to t times t to the power of 1 plus 1, which is 2, and then in the denominator also it will be 2. So that's how I get over here. It will be minus 10 and then j times t square by 2. And then integration of the third term, vi constant will be taken out, sine theta I will also be taken out, and integration of dt will be t, yeah, times j. And then there will also be a constant of integration d, which we have to find. So far, so good. Now we are at the final step, and that step is finding the value of the constant vector d. So we know from equation number 5 that at time t equal to 0, which means at initial time, it will give equation number 5 will give displacement will be equal to d. So let's call it as equation number 6. Yeah, and the idea is we have to get the value of d, and the hint is you will be given the initial coordinates of the projectile. So when we say the initial coordinates, say for example it was at 0 comma b, so this is the x value and this is the y value. So the displacement or the initial displacement will be equal to b times j. Yeah, so both 6 and 7 give the initial displacement, and therefore it should be easy to understand that we can equate 6 with 7, and which will lead to the constant d will be equal to b times j. So if we put the value of this d in equation number 5, we will get finally displacement will be equal to vi cos theta I t times I, plus in the bracket we will get minus 10 over 2, which can be written as minus 5 t square plus vi sine theta I t plus b times j. So let's apply what we have learned so far to the kind of problem that you may get. So this is a sample general problem and the solution for that. Say, for example, typically a question could be, how long will it take for the shell to fall back to the ground after the rocket explodes? So we have to find the time t. From the previous sheet, we have the expression for the displacement as given by this. And we have to see that when it hits the ground, the vertical component of the displacement will become 0. So that's the key point over here. So essentially what we are saying is this vertical component, which is times j, this vertical component should become equal to 0. And therefore, this equation seems to be quite familiar. It's a equation of the type, it's a quadratic equation, very similar to ax square plus bx plus c is equal to 0. So only difference is x is replaced by time. So we know that the solution for that is time t will be equal to minus b plus or minus square root of b square minus 4ac over 2a. But what are the values of a? So we have the value of a will be this one, and the value of b will be the constant that multiplies with t, and the value of c will be equal to b. Now, just as a matter of caution, there are two b's over here. We need to be very clear that this b over here is representing the quadratic equation, yeah, whereas the b that I have mentioned earlier was part of it was the vertical component of the initial displacement. So just you need to be clear. So with these values, we can put this value in the expression for t, and being a quadratic, it will have two values of t. Say, for example, there will be t1 and t2. So you need to check whether any value is not applicable. Say, for example, t may come out to be less than 0, so which is practically not possible. So therefore, then take the value which is higher than 0. This is just to give you one example. Now, another typical question that may be asked is something like this. How far will the shell land from its launching site? So we have to again make use of the expression for the displacement. And we know that when it is going to land, the vertical component of the displacement vector will be 0. So we know that this will be 0. So what remains is only the horizontal component. So we will get S will be equal to Vi cos theta I t times I. That will be the horizontal component of the displacement. And let's say from the previous slide, there were two values, t1 and t2, out of which t2 was ruled out due to whatever reason, say being negative or less than 0. So we are left with only one value, which is t1. So if we put that value of t1 in the expression for the displacement, you will get the horizontal distance as equal to this.